What do you mean by critically damped? Anybody remember?
So it doesn't oscillate. It just dies out real quick.
Okay. So the technical definition is that the system comes to its equilibrium position after one oscillation. So if we were to look at it graphically, let's look at it this way. So it comes to rest in one oscillation. And so you have the other one which is overdamped. Let me just list all of them.
Sir, you have a formula for that, sir? Can you do it?
So we get the formula.
All right.
So that's all I have in, so.
Yes, sir. Me.
Oh. So overdamp, the system takes a long time to reach equilibrium. Underdamp, the system oscillates. Many times before equilibrium. The best example I can give, two good examples of systems that have to be critically damped, is that you can buy your Audi. What number them reach now for the vehicle?
Q8, sir.
Q what?
Q8.
Q8. Right. You can buy an Audi Q8 and it dropping up a shake up a little bit down the road. It's dropping up at all and it's supposed to drop one time and come back to its equilibrium position. So all of the shocks inside of that system have to be critically damped. Right? So they have to fine tune those type of things. That's why you have to pay more money. The other damp system, like a fit, then it can be, the shocks can be a little bit less tuned so that it will oscillate wholly. Or it can be like a ladder. I don't know if you remember those. No, would know those cars. But long ago we saw some Russian car where they import ladder. Neil Massey used to import them. They used to call it ladder Massey. But the ladder then would have been today's Pro Box. Except say it was tough as tough as can be. And so if you drop in a pothole, you feel it in your head, you feel it in your spine because the shocks was almost non-existent. Right? So a critically damped system is supposed to go to equilibrium position after one oscillation. Right? So it must be shaking you up. The other system, if you have a system that your any analog meter that you have, or any meter that you have, that is going to go and spend the time oscillating around the final value before it settles. You want it to go to the value and stop. Right? You want the system, that analog system, to be critically damped as well. Right? So you want it to go to the value. So the spring must be such that the coil will enable it to go to the value and not oscillate too much. So it is a thing where we have systems where we would want it to be critically damped. All right. Some of them we don't care. And some of them we want them to be under damped and so forth. Now, the general transfer function of a system excuse me 1 second. Stop that thing from ringing. Okay, just gonna ring. All right. So now, the general transfer function for a system, which you're going to write down as having a little bit of a problem. Yeah, let's see if it's solved. Okay. All right, the general transfer function for a system is K over S squared plus 2 omega NS plus K squared. Sorry. We put K squared. Omega N squared. I'm going to take out this K. K, because I don't want it to be confused with the K in the problem. So the general transfer function of this system is given by the second order system. And you will see why it is that we are going to be spending our time talking about second order and first order systems in general. Now, if omega is equal to 1, I mean the damping, this not omega. Later is the damping ratio. It's called the damping ratio. Now, the damping ratio just tells you how much friction or how much opposition to the motion the system has. So if you think of yourself, well, picture a child on a swing, and then picture that you could have that child on the swing underwater. You would see that, and then think of the child on the swing, and you could be in condensed milk. Not Betty. Which one are the thick one? Anyhow, leave that alone. So the damping ratio tells you how much friction or how much opposition to the motion that you would have. So the damping ratio of the child on the swing in air, the damping ratio would be low. Whereas if the child was in condensed milk on a swing, and in the condensed milk, the damping ratio would be high. So we just need to make a note that if damping ratio is equal to 1 for critical damping. it's equal to 0 for a system that oscillates. It's between 0 and 1 for an underdamped system. And it's greater than 1 for an overdamped system. Yeah. So the system damping ratio tells you how much opposition to oscillation you would have. Omega n is the natural frequency of the system. So again, think of the child on the swing. So the child on the swing, if you push back the swing and let the swing go, it's going to oscillate at a frequency that is predetermined by the length of the swing and those kind of things, those parameters. Well, basically the length of the swing and where you are swinging. All right. So every system has a natural frequency. Every system has a natural frequency. So if you put some capacitor and inductors together, then the current and cause it to charge the capacitor and then close the switch. It's going to oscillate at a natural, the oscillation is going to be at a natural frequency, whether the oscillation is going to be critically damped or underdamped or whatever it is. But there's going to be a natural frequency, a frequency at which it oscillates if you don't interfere with it. Human beings also have frequencies that we give off. That's why we can't talk about boy, like the vibes that we get from the person or the person, because we can pick up the frequencies and we can know a person's intentions before, or whether or not our vibration at the time is in sync with that person's vibration or not. So, like I said, all bodies, there's a frequency of oscillation for all of these bodies. All right, so we were saying, so we just needed that background there to sort out this problem. So we want this system that we have here, the system that we discussed in the problem, to be critically damped. So our critically damped means that the output Y is going to behave a certain way. And that is what control is all about, control. Anything that you have control over, it is going to behave a certain way, dictated by you. So you put in a certain thing and the output is going to behave in a certain way. Desirable way. If it's uncontrollable, then the output is going to go to one or another of extremes that you don't want. And that is true of everything in life. So control means that the output is behaving in a way that you want. So let me get political and say, and of course we are seeing that around us right now. So a big battle for control. Anyhow, we are talking the maths. Go back to the maths. Imagine me knocking myself on my mouth. All right, so now let's go back to the problem now. It says find the value of the gain of the controller K, which will cause the output Y to be critically damped. So, so what we are going to do is let's go over here. And look at the problem. So we are going to so the transfer function of the system. Anybody remember how you find it now? Say yes. So we multiply these two. So it's going to be K over S squared plus 3S plus 1. And then we have a unity again. So we're going to have it as over 1 plus K over S squared plus 3S plus 1. All right, so that comes from when we have G and we have H. Then the transfer function is G over 1 plus GH. But in a unity gain system, H equal 1. So it's just G over 1 plus the G. All right, so if we simplify this, it's K over S squared plus 3S plus 1 all over, we put this over 1, so that's S squared plus 3S plus 1 plus K over S squared plus 3S plus 1. These cancel. So it equal to K over S squared plus 3S plus 1 plus K. So that's a transfer function of our system. And what we are going to compare it with, the denominators. So we're going to compare it with the general transfer function of the system. Now, if this system that we have here, if this is equal to 1, then our GS is going to be equal to omega n.
So let's put the S out of the denominator.
Oh, sorry. So when this is equal to 1, Then this is going to be omega n.
Omega.
Okay. Two important things will have effect on the problem. So zeta equal 1. Then this is what the transfer function is. So we're going to compare like with like in the denominator. Not, you will say that as we progress, so we have if we compare you have that 2 omega n is equal to 3 and 1 plus k is equal to omega n squared. If we compare the general transfer function with the transfer function that we have here. So we can use this to find our omega n and our k. So this implies omega n is equal to 3 over 2. And then 1 plus k is equal to 3 over 2 squared. Or k equal 3 over 2 squared minus 1. Where is my calculator? 9 over 4 minus 4 over 4. 1.25 dots. So the gain of the system has to be 1.25. So now, so what we are saying is in what we call the pole placement is that we find gains of our controller, because that if we look at the all of the systems that we have, one of the things that we will notice is that let me go back to the fellow doing the discussions about building your PID controller. And just all right, so I just let me see how me minimize it. Oh, okay. All right. Now, last week when I was talking about this brethren here, this Indian brethren who work at National Instruments, and he was talking about how he was building a PID controller. He was talking about how to build a PID controller and how to use the LabVIEW equipment, and he was going on and on and on. So I just want to focus on a section to explain just one little thing. Yeah, let me take it from here. So he says that tuning a PID controller, well, tuning any controller has an entire science behind it. And the science behind it is, as you are seeing now, the gains that you are going to be finding, although it has PID, but whatever we are doing and whatever controller we have, we're going to be filling in gains. We're going to be calculating gains using different methods and filling them in so that we can control the system. So he says that there's an entire science behind it. We're going to be using trial and error. He use trial and error or work it out. We do the calculations. All right.
Sir, now you remember.
Oh, you know, you remember. Oh, wait there, wait. Let me go back. Sorry there. Okay. So let me start again.
Create a control for the PID gains, and I can create a control for the output range. And now on the front panel, I can configure these settings in LabVIEW. Now, tuning a PID controller has an entire science behind it. You can mathematically determine what these values are based on a mathematical model of the plant itself. But more often than not, what I see is people basically using trial and error and experimentally determining what the optimal values are. And that's actually what I did in this case. So,
okay. So what I'm saying, let me see if I make it. It says that there's an entire science behind tuning a PID controller, and depends on your knowledge of the transfer function of the controller and the system, and then you can mathematically calculate the values of the gains that you are going to use there. All right, so we just mathematically said, that our system must behave this way, it must be critically damped, and then what are the values of the gain that we are going to put in to make it critically damped. All right, so in this particular, if we were given a PID controller, we would put the gain KC to be 1.25 and the other two to be 0. All right. With time, we will discuss what the integral time and derivative time and whatever else that needs to be put in there. But so that is what this course is about. The science behind calculating what are the values that we put in for the controller. And as he's correct, more often than not, people do it experimentally. And the reason why they do it experimentally is because everywhere you go, nobody knows the transfer function of the plant. So we're going to be discussing that as well. But people don't know the transfer function of whatever plant it is that they are controlling, so they have to use experimental methods to determine that. So if you're going to be working in a controlled environment, 9 chances out of 10, nobody don't know what the values of the plant, the transfer function of the plant that you're working with is. So you are going to be left in a little bit of a problem. So you most likely have to experimentally determine the values of the gains that you are calculating. Now, the plant that he is operating.
I've already seen a good response come from setting the proportional value to 0.6, the integral value to 0.05, and the derivative value to 0.04. For the output range, again, we're going to set that high output range, and I'm going to add a little easier to see. See as I ramp this up, I'm going to set this at about 2.3.
The system that he has, this is a motor. It's a fan. Fan is a motor. So you'd have to be able to calculate the transfer function of a motor and work out to be able to work out for the system what the transfer function of the entire system is. All right. So, and this National Instruments box over here is your controller. So your plant is a motor, and you're going to use it to control where the thing is. So I just wanted to point out that the course is just about calculating gains using different methods. All right. So please bear that in mind. So back to where we were. So we work out and we calculate the gain to be 1.25. All right. But in that brother named Rajiv, 9 chances out of 10 Rajiv took a control course at school. And never really two. Either never two penny wagon or never two like wagon. But that's a different story for us here. All right, so that is what we did here. So we'll just rehearse what we did here. So first of all, the problem says calculate the value of the gain of the controller K, so the output is critically damped. And so critically damped is a desired output, and so that is what control is about. Control is controlling the output. Anything at all you have if it's a car, if it's a child, you would have mapped your outputs and you put in a particular input and you expect to manipulate the input so that you get the desired output. So for the car is the desired speed, if it is son or daughter is the desired number of ones, or the desired PEP score so they can go to Campion so you can show off my other black friend them, etc. I will say Campion because people leave it from Montego Bay to go Campion. Don't know why. Montego Bay, St. Anne's, Manchester, Clarendon. All right. So, any questions up to there?
No, sir.
All right. So, let's do some more definitions, and then write down some formulas and some definitions of what we're going to need, some of the things that we are going to be controlling. So let us take Alright, so we want to define some parameters. We want to define maximum peak overshoot. Anybody remember what that is?
Sorry.
The highest point, sir.
Mm-mm. Technically correct. I understand what it in technically correct. It's the amount by which the maximum value of the output exceeds the final or stable value. So the peak overshoot, the final value is normalized as a 1. When we say normalized, mean that 1 is used as a standard. So the thing goes to 1. If it is 1,000, 12.5 or whatever the final value is, we're going to divide everything by, if it's 12.5 is the final value, we divide everybody by 12.5. So we're talking about one general thing. So the normalized output is 1. So the percentage by which the peak overshoots the final value. Now, the max peak overshoot, we can do the maths and come up with a formula for calculating peak overshoot. So it's E raised to the power all of those things. The damping ratio times pi over square root of 1 minus the damping ratio squared. So that's the definition of one parameter that we want to control, the maximum peak overshoot. For example, the kiln at the Jamalco, the normal operating temperature or the final value that we would want the kiln 1100 degrees Celsius. If it goes above 1700 degrees Celsius, then they start to lose product. Then, well, instead of aluminum, I think of chicken or cake. If the temperature got too high, then they burn up the cake. So the same thing, they burn up the aluminum. So they start to lose product. So you would want your peak overshoot, 1700 minus 1100 is 600. So it expresses a percentage is 6 over 11 times 100. That percentage, you don't want it to exceed that as your maximum peak overshoot. So in different industries, they are going to have different parameters. And one of the things is, yes. All right. Question?
Sir, could you repeat what you were saying a while ago?
Oh, I was saying that the bauxite kiln at Jamalco and Windalco and all the rest of them, the set point for the kiln is 1100 degrees Celsius. That's the operating temperature. So that's where you would want your final value when you set your temperature to be. If the kiln temperature goes to 1700 degrees Celsius. So it overshoots 1100 and goes up to 1700 degrees Celsius. Then you are going to lose product. All right. You start burn up the aluminum and it becomes something else that you don't want. So 1700 degrees is the maximum that you want it to overshoot. You don't want it to reach 1700. So you are going to try to control the output so that it never reaches 1700. It can overshoot, but not reach 1700. That's the maximum value that you would be working towards. And we are saying that the maximum peak overshoot is, you can calculate using the damping ratio of the system is E raised to the negative. The damping ratio pi over 1 minus the damping ratio squared, square root of all of that. So that is the formula for maximum peak overshoot. The rise time. Is the time taken to reach the final value for the first time. This is for overdamp system. Underdamp system, sorry. So it's the time it takes to reach the final value for the first time. So this is for underdamp systems. Or time taken to reach 90% of the final value so this is first order or overdamp systems. All right, so the rise time is the time it takes to reach 90% of the final value. So or the final value for the first time. So again, let me show you where at the end of this we talk about where we get these formulas from.
May I want to share screen?
Sir, is it just me or I'm not seeing anything on the screen?
I just said the screen is paused.
Oh. Oh,
Just saw it.
okay.
So from when you did pause, by the way?
You just got blank.
Oh,
Even now too.
yeah, I realize why. I was trying to bring up something while you were looking at the screen, but let me just bring it up first, and then.
I think that caused because of the system probably slow, sir.
I did not pay the bill on time in November, and I did not realize that the system, the longer it doesn't, you're not paying it. The longer I don't pay it, the more the system degrade. And when I finally pay the bill, they tell me say they forget to upgrade it, and even now still having problems.
Jaja.
So throw me the switch from Digicel where you could have made the bill go on for 2-3 months and then pay everything one time. Really think it was the same thing with Flow. Because I never said them cut off anything, but my internet was just getting worse and worse and worse. And then it's them tell me when we call them, say, oh, you never pay the bill on time, so system start make this system degrade. And then when you pay the bill, now they forget to put it back to where it was. So I don't know. All right. The formula for rise time.
Sir,
Mr. Gone again.
sir, sometimes when you have too much things running in the background, Zoom tend to do that, sir. Yeah, shit.
But we don't do much. There's two things we have in the background. This that I'm bringing up here. So rise time. So the formula for rise time. 1 over omega d tan inverse within minus square root of 1 minus the damping ratio squared over the damping ratio squared. So this is the formula for rise time. Here what? I am just going to use less things. So let me just write it down instead of bringing it up on.
Yes, sir. Write it down because I'm not seeing. It's kind of blurry.
Right. All right.
Doesn't have omega what right there, so.
All right. Let's write it on the screen.
All right, can I share the document, sir?
Huh?
Can you share the document?
Yeah, we'll at the end of the class.
Okay.
What is that? It's just a test paper. Just an exam.
Okay.
All right, so let me write it down instead of sharing. All right, so the formula for rise time is TR. That's the rise time, so I should put TR up here. T subscript R is 1 over omega d tan inverse minus 1 minus damping ratio squared square root over the damping ratio squared. And omega d is the damped so when you have the child in the condensed milk, the frequency at which that swing oscillates, that is the damped frequency. Right, whatever medium the thing is oscillating and whatever is holding it back, then that frequency is a damped frequency. And omega d is equal to square root of 1 minus omega n 1 minus the damping ratio squared. These formulas are not for your swatting. And well, in this paradigm, it wouldn't make sense for you to tell you that because how would I prevent you from not looking in a book anyway? All right, so the damped the rise time, like we say, is the time it takes to reach. So if we have a system, my rise time is the time it takes to reach the final value for the first time, or if it is a system that is first order, then it theoretically never reaches. So the rise time is the time it takes to reach 90% of the final value. So this is a second order system or higher. It's a first order. So that is rise time.
Sir Fraser, question. For the first formula, what is the symbol after the 1 minus?
This first formula. This here?
The one for the
This here?
rise time. Yes, sir.
Rise. This symbol here?
Yes, sir.
The damping ratio. The Greek, the official symbol is the Greek letter neta, not neta. But I can make that symbol, so I just use that this one here over the years.
Okay, sir. All right, thank you.
So use any symbol that you want. As a matter of fact, you should just use D.
Okay, then, sir.
All right. The third thing that we might want to control, apart from the peak and the rise time, third thing that we might want to control, maximum peak overshoot, we might want to control the peak time. Everybody still there? Something just disappear from the screen.
Yes, sir, we're here.
Yes, sir.
Yes, sir. See the ball.
Everything just disappear from off the screen, so I don't know. They usually assign, I see the internet here, guard out a little bit or not. Yeah, we might have to go outside and run everybody off of the internet. All right, so peak time is the time taken to reach the maximum value. All right, so that is straightforward enough. So peak time is equal to pi divided by the damp frequency, which is pi over omega n 1 minus the damping ratio squared. All right, and the fourth one. The one that's most, if we're doing the actual system, this is the one that would be used the most, the settling time. And that is the time taken to reach within 5%. And that is a nominal value. What I mean by nominal value is that these definitions that I'm giving are not definitions that are carved in stone. You know, like definition with resistance where is the ratio of voltage to current if everything else, if the temperature remains constant. That's a definition that's carved in stone. Cycling time to reach 5%. The 5% is not carved in stone. Some people have 4%, 2%, 1%, depending on the equipment that they're working with and how they want the system to operate. So the formula for cycling time so 5% of the final value. So you want it to reach within 5% of the final value. So this leads to the formula being 4 over omega n. This value of 4 would change if we change the 5%. So suppose we want 2% cycling time, then I think this number goes up to 5. Now, all of these come from, see, I was trying to send a textbook, I don't know if it reach. All of these come from yeah, it said. You can calculate it from the response of all of these formulas from the response of the system. Because this response of the system that is oscillatory is y equal a e to the minus a L equal to a to the minus a t sine bt. So to find, for example, rise time, you may equate this formula to 1 and solve, or you equate it to the other one to 0.9 and solve. If you want to find the peak time, that's the maximum value, so you differentiate this and make it equal to 0 and solve, and so forth and so on. All right. You want to find the maximum value. When you find t, you plug it back into the equation, all of the calculus that you have learned, but we're not going through all of the calculus that you have learned to derive these things because somebody do it already, so we don't have to do it again. When you see them, tell them thanks. All right, so those are the definitions of the parameters that we want to control in a system. So we can want the system to be critically damped. We can want the system to be to have a particular rise time, have a particular overshoot, and so forth and so on. Now, a rule of thumb is so a rule of thumb, which is means it's not a real rule. If we want to control k parameters, we need k gains. So in other words, suppose we want to control two things, peak overshoot and cycling time, then we need 2 gains. If we want to control peak overshoot and cycling time and peak time, There's three things we want to control, then we need three gains. Basically, it's not a rule that says that this must be done, but this is just a rule of thumb that if we're using pole placement, then that is something that we need to bear in mind. All right. So let's take another problem. And let's see if we can use the definitions that we have here and work with them. And so all right. So problem that we want to say that we have this and we have our controller. All right. So we want to find the gains of the controller, which will make the system have 10% overshoot and a cycling time of half a second. So what we are going to put in is that we need two gains. So now here begin it the real pole placement, because what pole placement is all about is that, well, what we're going to do here, find the gain such that we can get the behavior that we want. Now, if I go back to the video, what Ramjeet said that he put in some values experimentally and he got a good response. Right? Good response means it looked like something that he can work with. Here we are working towards an exact response. That is, we need to find out what are the values that we put in to get the gains to give us 10% overshoot and cycling time of half a second. All right, so we're not cycling for good. This is what we want, and so we're going to work out the values of K1 and K2 that will give us what we want. So tell me when I can start working out the problem. Everybody there? Hello?
Yes, sir.
Oh. You could have gone again.
There you go.
Yeah, I was telling you to tell me when I can start working out the problem.
Yeah, you can start, sir.
All right. So first thing, peak overshoot. Let me calculator. Forget so we went to need the calculator. So we're going to fill in the values. 10% overshoot means that this thing here is equal to 0.1. So we can, everything else there is known because there's only pi alone in there. We can work out the damping ratio. So tell me how we go about solving this problem here now. No, see the calculator here.
So ln both sides.
All right, so ln both sides. And if ln both sides, then it's just what is in the denominator will come out. So that's minus over 1 minus damping ratio squared is equal to ln 0.1. We're going to square everything to get rid of the square root. So I give me damping ratio squared over pi squared over 1 minus damping ratio squared is equal to put the ln squared 0.1 here. And we're going to be using this so often. When we reach here, we're going to replace the 0.1 by whatever the peak is. So we cross multiply. So ln squared 0.1, 1 minus the damping ratio squared is equal to the damping ratio squared pi squared. So ln squared 0.1 minus damping ratio ln squared 0.1 is equal to damping ratio squared pi squared. So carry this cross here. So we get pi squared damping ratio squared plus damping ratio squared ln squared 0.1 is equal to ln squared 0.1. So take the damping ratio out of the bracket, pi squared plus ln squared 0.1 is equal to ln squared 0.1. So damping ratio squared is equal to ln squared 0.1 divided by pi squared plus ln squared 0.1. And we just shift everything across. Or the damping ratio is equal to the square root of ln squared 0.1 over pi squared plus ln squared 0.1, or the general formula. So the damping ratio is going to be equal to ln squared mp over pi squared plus ln squared. Somebody can work out that for me? Oh, I should point out that subsequent classes we're going to use MATLAB. So I hear that the school is supposed to be getting MATLAB. So hopefully we can stay at Riyadh and access the MATLAB. Anybody work it out? Me work it out, I get 0.591, but I'm usually wrong, so somebody needs to check and see if I get the same thing. My maths teacher always tell me, sir, make sure me finish every maths test, because me always get every single answer that me have to calculate is always wrong. So live with it, like sore foot. You have to just live with it. So somebody check and see if it is 0.591 for me.
Yes, sir, that's the answer I got.
All right.
Sir, in the standardized formula, MP, right, sir? What was the question? The first part of the question, we were supposed to calculate for a peak overshoot of 5%?
10%.
10%. So if we put the 0.1, oh. Okay, sir. So could you scroll down? Back to the formula. Oh, okay, sir. Yeah, I thought there were two different things. Thank you.
Okay. All right, so we go back to the specification for the question. It says that the settling time was 0.5 seconds. So we know that settling time is 4 divided by damping ratio times omega n. So if we make omega n the subject of the formula here, omega n would be equal to 4 over the damping ratio times the settling time. So this is 4 divided by the damping ratio, which we just calculated as 0.591 times the settling time, which was told as half a second.
Sir, I got 13.5.
All right, 13.5. Omega n. Okay, so now we have to go back to our original formula. This says GS is equal to omega n over s squared plus 2 omega n s plus omega n squared. I'm filling the values. We're not really so concerned with the top as with the denominator. So it's s squared plus 2 times 0.591 times 13.5 s plus 13.5 squared. That's 13.5 over s squared plus 2 times 0.591 times 13.5. Get 15.96. Now we work with 15.96. If we were in the office, we'd write those 16. But we're writing down 15.96 because we're in class. So. Plus 13.5 squared. That's 182.25. So this is our desired transfer function.
Sir, for the solution, I got negative 7.98 plus or minus 10.89i.
For this?
For the bottom.
Okay. But we don't really, when we're doing full pole placement, we're going to talk about finding the poles for this system, which is what you found. But for the initial purposes of this problem now, we don't really need it so much.
Oh, okay, sir.
All right. So now, what we have to do now is look at this find the transfer function of the system that we have. So what we are going to be doing is using the gains K1 and K2 to transform this system into this system that we want down here. So the poles of this, the K is going to be such that it change the values on our system. So this is our system that we have. So it's K1 plus K2 S. As 1 over S squared plus 4S plus 3. And So our system, when we multiply, we're going to get K1 plus K2S on the denominator over S squared plus 4S plus 3 all over one over 1 plus K1 plus K2S over S squared plus 4S plus 3. So that's K1 plus K2S over S squared plus 4S plus 3 all over S squared plus 4S plus 3 plus K1 plus K2S S squared plus 4S plus 3. So these cancel, and our transfer function is K1 plus K2S over S squared, and then we're going to put K1 and K2, so that is going K2S plus 4S, so that is 4 plus K2S, and then 3 plus K1. So what we are saying is that we can set the values of the K so that our transfer function that we have for the system, the K's can be used to change the transfer function of the system to the desired transfer function, which is S squared plus 15.96 S plus 182.25. So compare S squared plus 4 plus K2 S plus 3 plus K1 and S squared plus 15.96 S plus 182.25. Those are the two denominators that we are comparing. So, as we want you to see now, is that we're going to compare the 4 plus K2 with the 15 and the 3 plus K1 with the 182.5. So therefore now 4 plus K2 is equal to 15.96. So K2 is equal to 15.96 minus 4, which is 11.96. So approximately 12. And 3 plus K1 is equal to 182.25. That's 179.25. So these will be my two gains. So those are the two values that you put in the controller to find for the system. Alright, I want to work out one more problem for this evening. Next week, we want to show you how to use MATLAB and do these calculations.
Sir,
Mhm.
yeah, that different percentage overshoot. We just have to change that in the damping ratio formula and recalculate the new ratio.
Yeah.
Thanks, sir.
Mhm. Alright, so we're going to use the same thing, but I just wanted to illustrate an important point. An important point in the calculation concerning calculation which involve rise time. So we're going to use the same system and we want to calculate it's two things controlling rise time and overshoot again. So we are going to we're going to go back through set of calculations. Now, the seconds that we have here, in depending on the industry, like with the bauxite industry, the rise time is usually somewhere of the order of 10 to 15 minutes. Time it takes the temperature to reach, I was saying is 1100. Time it takes temperature to reach 1100 degrees. Because as if you think about it, the steeper the rise, let's say you turn on, think of it as well heat, and you turn it on such a point that it rises quickly, very quickly. Then the chances of it overshooting are also having a massive overshoot is much less than if you took a longer time. So whenever we start talking about controlling parameters, the parameters that we are controlling, right? Like I said, we also have to be realistic, and some of them we might not be able to achieve. But more on that. All right, so rise time of 2 seconds and overshoot of 20%. So we go back to the formula. What did we say? It was square root of ln mp squared. I put the square over 1 plus pi squared. Sorry. So square root of ln mp. Let me make sure I'm right. Ln squared mp over the rise time pi squared plus ln squared mp. Make sure I have it right. We're so far up with it. So that is going to be equal to ln squared 0.2 over pi squared plus ln squared 0.2.
Point 456.
Yeah, 0.456. All right, so now for rise time. So we're going to have to use a little bit of the trigonometry we already learned. Our rise time is 1 over omega n 1 minus damping ratio squared tan inverse minus 1 minus the damping ratio squared over the damping ratio squared. Now we want omega n. So omega n is going to be equal to 1 over rise time. So switch places. Square root of 1 minus damping ratio squared tan inverse minus 1 minus damping ratio squared over damping ratio squared. So that's 1 over the damping ratio squared is 2 times the square root of 1 minus 0.456 squared tan inverse minus 1 minus 0.456 squared over 0.456 squared. All right. Now, so this part here, what was the part before the tan inverse. That is 1 divided by 2 times square root bracket 1 minus 0.456 squared close bracket equal reciprocal I get 1.78. That's what I get. 1.7799 595 whatever. Now, here's the part. So 1 minus 0.456 squared divided by 0.456 squared. When you reach up to here, tell me so we can have a little discussion. When you reach, so we can talk about this.
Yes, sir.
All right. First thing, tan inverse of negative 3.809. We have to put our calculator in radian mode because the answer must be in radians. Right? Not degrees. So I have to change the calculator to radian mode. Then we have to find, so now, when we convert to radian mode, all right, so we're going to tan inverse the radian mode. What you get as your answer?
Sir, the tan inverse is the 1.78. All of this tan inverse are just the tan inverse, radians are just the tan inverse part of your radians.
Well, yeah, just the tan inverse part, but when you multiply by 1.78, it won't be a problem. But tell me what you get for the tan inverse.
So 1.3, 1.
1.31, negative 1.31.
Yes, sir.
Correct?
Yes, sir. That's what I got.
You get negative 1.3.
Yes, sir. And the final answer would be negative 2.339.
You cannot get a negative answer. So here what? So we have to go back to some of the trigonometry that you did learn, whichever part of the world you did learn it in. So we as lecturer famous to say, oh, you did learn it in a third form at high school. Well, me never learned this in a third form at high school. So remember now, we have to because omega n natural frequency cannot be a negative value. So we have to remember, first of all, so the whole entire thing around the circle, the unit circle, is 2 pi. Negative 1.31. We have to remember where exactly does that fall. So negative 1.31, if we took it, it would fall in this quadrant here. So we have to convert that to a positive answer.
Sir, 4.957.
All right. What you did? Subtract it from 2 pi?
Sir, I did end up find the positive end for the 7
All right, so
point.
the whole entire thing around is 2 pi. So going back this way, we have negative 1.31. So what is it going this way? So it is going to be, so we convert to positive value. So we just say 2 pi minus 1.31. How much you say again?
Sir, I got 4.97.
4.97. So omega n is going to be equal to 1.78 multiplied by 4.97.
For that, I got 8.85.
All right, so just bear in mind this little part here.
Sir, could you go back over the part with the 1 over 2 times the root of 1 minus 0.456 squared?
This part here? No, but all I did was just do the calculation. I get 1.78. Isn't that you get?
I'm going to work it again, sir.
Sir, may I get 0.631, sir, that may I get?
For this part here, sir?
Yeah, 1.74. We'll check again.
I'm telling you, most likely it's me wrong, so.
So right now the whole is freeze up in there.
No, we're not doing anything, you know, I was there working out 1.78.
Oh.
I'm getting the wrong answer a couple times. Why did I get 0.56 this wrong?
Sir, I got 0.562, so I'm...
Alright, so that is correct.
Yep.
So, sorry.
Yes, sir, correct.
So this is
D'Angelo, that's what you got?
I get 0.562.
Yeah, 0.56. I know it's...
Alright, so this is 0.562.
So the final answer is 2.79.
2.79. Alright, so now our desired n over s squared plus 2 times 0.456 omega n 2.79 s plus omega n squared. That's omega n over s squared plus 2 summation omega n s plus omega n squared. So that's omega n over s squared plus I got 2.54 for this part. So tell me if that's what you get.
Same thing, sir.
And it was the next part, 2.79 squared,
7.78.
7.78. All right, and we're comparing it with, we don't have to work out about the transfer function again, the same transfer function as we had before, which part is there? S plus
I have to reshare, sir. Just kick you out just now.
yeah, I realize. Run them way off of internet because anyhow, of course, if we taking business out the road.
I'll go on with this.
Like I hate that for the class, man.
Huh?
Like I hate that for the class.
Yeah, but maybe if you don't write so I have to click someone look at it, kick off.
Yeah, yeah.
I don't know if you